I'm very happy that she put into the picture golf. It was a kind of middle term between Leibniz and the others. The reason why I didn't mention golf was that though he was a mathematician and was a very strong admirer of the mathematical methods put everywhere, well, he never developed a logic to calculus. This is why he didn't fall into the picture. Well, you know about that. And but it was very good to point out to the fact that one cannot go on looking at these notational systems without knowledge of the semiotic of their time. Because the theory of science is so important, at least since John Locke, whose book was studied as if it were a work of logic everywhere in Europe, said that there was an equation between logicae and semioticae. And this changed the destiny of logic in many countries in Europe, and especially in Protestant countries, among which Germany was. This is one thing, you did very well to go with this. And the other point I liked is that you went deeper into the question of language and metaphors in Lambert. Yes, you are right. Lambert wrote this big, important book divided in different sections. The Dianology, which is the first, more or less corresponds to a logical treatise, but then there was the semiotic and the archaeology of theory of truth, and then he was the inventor of the word phenomenology, because there was a doctrine of errors in this part of the book. This second part has much to say, as you showed, on the question of language. But here, in a way, I want to keep separate the two issues, because with metaphors, you have to keep in mind meanings. And so here, there is a problem of the sign being the word written or spoken, and the double thing you find everywhere in Leibniz too, and the correspondence with an ideas and with a thing. They sometimes find the two references in the same passage, almost in the same line. And this is another problem. So, I think you have read it, and I think you have work to do of your own, and that's all I have to say on what because you made no objections, really, you made extensions, and they were very good, and one should extend the so that's all.
Perfect. Actually, why don't we take questions now for Professor Capozzi to see, to keep the discussion focused on this, and then we'll move to the Yes.
Yes, I have a general question for you. And what I would say is it sounds very plausible, the thesis that people are arguing, that science is the primary sense when dealing with formal reasoning. But there does seem to be little evidence against this, which is the fact that there have been a great number of very successful blind mathematicians, which to me is actually surprising. For example, Ronald Fisher, who thinks statistician is virtually blind. And recently there's Larry Wass, who is very distinguished in automated theorem proving, and he, I think, was blind from birth. Now, I know this issue was discussed in the 17th and 18th century, I think by Leibniz as well. In fact, I remember that in the new essays, I think Leibniz actually said that blind people criticize Locke and say blind people can learn what we think. So, how much was the issue of blind mathematicians discussed, and what did people conclude at that time?
Thank you for your question. The question of being born blind or and the whole, which takes into account what Locke and all the others were saying about these things. The fact that there were blind mathematicians, well, there was a very famous blind mathematician, blind in his old age, was Euler first, but you were mentioning the people born blind. Then there was a theory of sensibility according to which there was the senses were one vicarious of the other. So if you had the sense of touch, so you had an idea of space, and having an idea of space in a way helped. And then the problem, you could hear what people told you, and you could touch things, move around in space. Indeed, you were notified, with the meanings of what to say. You could move. You had a special, anyway, as far as space was concerned, and geometry and so on, you had the sense of touch, and this helped. In fact, what was really difficult to explain was the loss of the hearing and of the speaking capacity, because people thought that in this case, provided that, given they were the first schools for the deaf at the time, and the big question was, should we teach them the sign language or to pronounce some kind of sounds to communicate with others and to look at the mouth of people and say how to speak. When they arrived to a kind of language, would they have abstract ideas, or would they always signify with a single thing, just making generalization from memory rather than having. So this about the question of mathematicians, there is very little written. What they wrote about very much, as you mentioned from Locke, is the cases of people who were born blind and then acquired the sight. There was the famous problem of Molyneux. How someone born blind, what happens when he sees? So the other thing which was mentioned, I remember probably by you, Chiara, or by someone, other people, about people who had no language, not because they had no hearing or the capacity to speak, but because they were in the wilderness and then were able to sleep. But these were things more than the question of mathematics. So probably this should need more time.
Other questions? Yes. Could come forward. Sorry.
I would be willing to try here. So I would have thought that I expected to hear more about the difference between iconic written language and non-iconic written language, because that was a big issue concerning memory among mathematicians. The idea was that if you had an iconic written language, that you could keep the objects of reasoning before your mind more continuously, and lapses of rigor would be in these cases of discontinuity, that sort, where one's mental attention somehow wandered from the topic of investigation. Now, what occurs to me is that there doesn't seem to be any parallel distinction on the side of oral language. What would the distinction between iconic and non-iconic come to in oral language? So it seemed to me that would be a very important asymmetry, but I didn't get anything from what you were saying about that.
Much of what I said,
Let me talk.
part of what you said, is kind of research I'm doing about which, although on the side and Fouquet writes a part of metaphysics where it was all the cognitive things and part of logic. So they decided to have a reproduction of the logic part, and they missed the pieces on the deaf people, and which is not something, just for conversation piece, but it is important for someone like that. So you are right, you cannot make this difference, and this is why logicians concentrate on vision in a way, because they have to do words. In logic, well, I just mentioned that, they have diagrams, which are analogical way of putting, because it's not like geometrical diagrams, which depict in a way the object, if any. And the problem is that if, apart from Euler, but very sophisticated diagrams by Lambert himself, by Leibniz, and other people, but that was a kind, an analogy. You see two circles, one in the other, and then you can pick either a universal affirmative proposition or a particular one, in the inverse way. But then the algebraic model was preferred, not only because it was iconic, and then it was in very little space, all the things. These are cognitive properties of the items which are good to have, but also because they were not decided whether they would have intentional calculi or extensional ones. For instance, Fouquet wanted to depict in an intentional way a universal proposition, affirmative. And then we should say that the subject contained the predicate. So how could you put it with two circles when the subject is smaller and the predicate is larger? Something like that, was discussed about. So if you write down algebraic symbols, we can play both ways, and the interpretation changes. I think this. On the other part, certainly, there is no iconic or not iconic because it is a visual language. Apart from what you are suggesting to the audience, because and this is why the suggestion is important for people who are the professionals of speaking aloud, and also for the scholars, because the word can make you see what is not present. That was what Cicero in rhetoric called an epiga. It was a quality of language to me. And so what is better when you have to discover something, to see something which is not present, so that you project your thought and try to there is seeing also with the language, because while I'm speaking, I can give you the picture, as one says, of something in the past or something in the future, and then you see, and this is why a good speaker wanted to win the audience, tries to shift the attention to something that the audience knows. For instance, well, this is like a father with a child, and then one is moved towards. These people were trying to have rules for the scholars, and let's try to do something in this way. But you're right, there is no
What's interesting is that in the 19th century, just the opposite view was taken. So Piano, when he was inventing his formula, said, we have to choose symbols that have no association whatever with what they stand for. Because if there's an association, people will import without recognizing it. Certain assumptions
without imagination, as the Leibniz said, without embarrassing imagination. This is the good thing with I would not say symbols. They are signs, they are characters. Otherwise, as Ian was saying before, there's nothing symbolic, because symbol means standing for, while there are things which, if you got all these paper with dots and things for us to see it, relation, syntactical relation, okay, but you have to put something on the paper or project it. There are signs.
Okay. Well, was there anything you know of that made a connection between this change in what was required by Ricker? I mean, from iconic representation to completely conventional representation. Okay. I mean,
Well, you see,
They
I
have
think
connection with
the problem is that once, usually, this problem is taken to concern mathematics, which is a problem. The other problem for them was logic, which would apply to anything. So, even in your very nice form, you spoke in general, but the problem was always the representation of some mathematical object or not mathematical object. It was always, a reference to that. And I think this made, something more and different.
Okay, now, the Lord.
I'm shutting up.
No, you're fine, stay put. You cover.
Okay. Thank you for your points. I agree with all of them. Actually, I learned a lot from your remarks. I agree with you. If I am not wrong, you, so to say, you see Aristotle's position as different from that of Galen, since Aristotle's view on science is a pluralistic one, and mathematics as not the main position in it, while Galen's view on science is a monistic one, and mathematics as the position of a standard. I basically agree. I mean, I think you are certainly right. It's a very good point. As far as Aristotle is concerned, certainly his distinction implies some hierarchy. I mean, sciences are not simply different. There is a hierarchy. They are ordered according to a hierarchy. And actually, I think, there is a famous passage from the Censo where Aristotle basically says medicine is scientific since it is close to natural philosophy, and it is not scientific because it implies a certain practice, more or less, in the same. It is quite, sensible. Interest of Galen's position is to develop something like a conjectural but scientific treatment of accidental practice. The closest parallel is with ethics, indeed. And you are certainly right. Feeble is perhaps not the right word to characterize, for example, medicine in Aristotle's overall view. If I'm not wrong, Aristotle used the word malakos in order to characterize ethics, i.e. not feeble, but so to say, softer than mathematics and so on. So, but basically, I agree with you. There are certainly two radically different views on medicine, on sciences. By the way, I don't really know if Galen was really well acquainted with mathematics. I mean, he had certainly good knowledge of Euclid's elements, but certainly I don't think he was well acquainted with Archimedes. He has an ideology of mathematics rather than a real practice of it. There is a further problem, I think, when we talk about the ideal of mathematical axiomatization in Aristotle, we should be aware that mathematical axiomatization was, so to say, being developed when Aristotle wrote his works. So it's very difficult to have a clear idea about mathematics before Euclid, of course, because we have virtually nothing. I mean, we have several passages dealing with mathematics, with Hippocrates, with with the method of Hippocrates and so on, but Hippocrates the mathematician indeed, not Hippocrates the doctor. But there is a certain obscurity.
Okay, questions? Yes, please. Come, please, if you like.
thinking about law.
Yeah.
Because in legal reasoning, you know, it comes down to cases and individuals have their fate decided, so individuals are irreducible. And I was thinking of a book that I have been reading for 40 years by Edward Levy, who was the president of the University of Chicago when I went there, called An Introduction to Legal Reasoning. What he says is that the American system is well constructed because it has three levels. There's the level of case law, which is really the organization of particulars, and it is a moving system of classification. Because in social organization, things change more quickly than in natural organization. Then there's the level of federal law, where laws can be introduced or removed, but it's very difficult, and it requires a lot of national deliberation. And then there's the level of constitutional law, which is very abstract, so that the meaning of those laws is in some ways indeterminate, in some ways determined. And those laws don't change. So that when you have the three levels together, it's very effective. And then I wondered what that would look like if there's something like that in medical reasoning. And I also wondered if there's some analog for logic. Some analog for logic. And what we might identify, you know, like pure logic, applied logic, like applying logic to physics, let's say, and then some topics.
Well, thank you. That's most interesting question. Well, as far as the ancient world is concerned, my competence and with ancient philosophy actually, certainly this analysis is very limited. I mean, unfortunately, we do not have almost anything about ancient philosophy and law, because we have lots of texts, but nobody really focused on these texts. That's really good. But certainly, medicine and rhetoric, which were very closely connected with law in the ancient world, share the same epistemic problems. And for some reason, I mean, when the Romans developed their legal system, they were very much interested in the same concept which we find in ancient medicine, i.e. classification, the limits of classification, conjectural reasoning, and so on. And rhetoric and medicine were extremely closely connected in antiquity. Indeed, physicians wanted to stress their difference from people who practice rhetoric. But this very fact shows that the connection was widely perceived. And certainly there was certainly there were also further elements of connection. For example, the use of memory in both rhetoric and rhetoric as connected to law, and in medicine. So much. I was very happy when I had Mirella Capozzi's paper, because most of these problems also emerged in ancient medicine and in ancient rhetoric. So, as far as the use of logic, if I understood your point, I mean, certainly there is, at least in some of ancient physicians, the effort to develop at the same time a general structure for their discipline, and to investigate how some rules allow But certainly, I mean, the overall analogy between law, rhetoric, and I'll say another very aesthetically very interesting, well, science in the broad sense, developed in antiquity was astrology. Maybe it is not a science in our eyes, but let's just think about the very fact that Ptolemy wrote a whole book on astrology, trying to show that astrology can be treated as a science via conjectural thinking. And it is more or less what we find in rhetoric, in medicine, in all these spurious sciences.
Another question?
I think
All right, so then,
I promised to say something about the consistency of electrons.
right, sure, no, there's no question for Jan. Okay, so we'll move to Jan.
So I tried to phrase this thing in terms of maybe more familiar to. In about 33, Gödel and Jensen found that you can translate classical arithmetic to intuitionistic arithmetic, and especially the consistency of classical arithmetic reduces to that of intuitionistic. Now then, Jensen found a proof in 35, which, in my opinion, and I think I'm in good company, uses implicitly Browner's principle of bar induction on the constructive transfinite order. Then Gödel was very upset about this thing. It was in Princeton with Berners, and they were going through Jensen's proof and sending letters to Jensen. This is no good, this is no good. And so Gödel had to find a view of his own. So he did this dialectical interpretation of intuitionistic arithmetic, in which you translate arithmetic into a hierarchy of primitive recursive functionals. That was the dialectical thing. He did it from 38 on. Yeah, in 58, well, that was in the Berners question. Anyway, so consistency of arithmetic follows from the termination of the computation of the values of these primitive recursive functions. And Bill Power found this proof in the late 60s. Gödel was very upset by actually corresponding with Power, and he referred to what Gödel said. He said, you should give a much simpler proof, this is no good, and so on. So the last thing he said to Howard about 1972, have you figured out a simple proof? So that's one way of looking at it. Of course, I mean, it transcends in a certain way gamma arithmetic, because it uses a constructive, this intuitionistic transfinite induction, but it's an induction on a primitive recursively defined predicate. So it is, in my opinion, a remarkable simplification. That's a small anecdote. And Capozzi proved the consistency of pi-1-1 comprehension in second order arithmetic in the early 50s. Then there was a review in the Zentralblatt in which the reviewer said, this is nonsense because from this result the consistency of gamma arithmetic follows, and Gödel showed it not to work. So.
Yes. Oh, I'm sorry. All right. 1, 2, 3, 4, 5, 6. No, and that will be it, and we will then reconvene.
Just to say that Aristotle was well aware of the threefold of equations. In fact, he needed it, because in the second part of the paraanalytics, after section 26, when he develops his logical discovery, he describes this process. If you want to discover proof of something, you start from what you want to prove first. Then, by eventually, or induction, you find major trends or parameters. But then stop, because this must be a case. Now, we're going to see here again manifest principle. So, you stop here, and so on. So you see, he assumes that derivation must be.
Well, this just shows what the bad, lousy Aristotelian scholar I am. I just read the initial parts which explain the principles, so, and left for students to work their question. So, thank you very much. I'll make no comments.
Okay, so my question was about your reasons about reduction ad absurdum. Reduction ad absurdum.
It makes an echo.
Okay.
You put away the microphone there.
So it's better.
Just put away the microphone, please. Okay.
So there is something which seems not really contrary, but which is in tension with the result unknown in natural deduction of self-image, showing that we can always, in a classical proof, put the reduction ad absurdum only one instance in the end of the proof, but only with the for, only without for all. So there is something which seems,
No, that's wrong. This is a counter example. You need to without penalty to do that.
the point is that there is a result of setting
Yes.
saying that if you are not for quantifiers in your language, you can always have only one reduction ad absurdum as only one on the last rule of the proof.
Yes.
But this doesn't.
That's wrong. That's wrong.
Yes.
You need two for that. You can do it in a second. See, it's quite obvious that this will not happen. There's no way of I said that so I said very carefully that you can reduce several indirect proofs in one derivation branch into just one, but you will need several, so that's the indirect. You will, as this example shows, you will need several, but on different branches. The result is wrong.
Okay, but in a way, even if it's wrong, I don't understand, because here you got...
Here it works. Here it works, but this is because Aristotle's logic is a bit special.
Okay.
Okay.
There are no connected, so that's why.
I don't remember what we're thinking.
Yeah, this is really just to encourage you to be a bit more precise about what you're claiming for the two-dimensional representation. I mean, there are just a couple of cases. I mean, I'm happy to grant that for the purpose of proving a lot of proof-theoretic results, that a two-dimensional proof system is the most useful. But for example, for proving a lot of semantic results about the semantics of systems, it's often much more convenient to have an axiomatic presentation of the system. And also, simply when one thinks about how proofs are normally given in mathematics and in the meta theory and logic, I mean, they're normally given basically as linear proofs. But I mean, if you look, they're basically written in prose with formulas, and I mean, they're not written. I mean, of course, there are diagrams from time to time, but it's fundamentally a narrative presentation of the proofs. And I mean, it seems to me that's motivated by the fact that there are all these memory limitations on us, which mean that when we actually go through a particular two-dimensional proof to see why it works, we have to go through in some kind of order, and we have to trace a path through it. And so it seems to me that when the proof is there, not as an object of study, but simply to convince you of the result, the normal mode of presentation is by and large a linear one with occasional two-dimensional illustrations?
Well, an extreme case of this is, of course, Wein's proof. So one mathematician proves one thing, and another one proves this one thing leads to another, and so on. And in the end, we don't have any idea what the assumptions behind the result are. So that's just what happens. It can happen that, typically, well, someone finds, well, I assume A, and then I get to some C. And then you find that there was another mathematician who got this C from some B. So then you say, aha, I make it like this. And then you just sort of forget the work of these mathematicians. So these kind of things happen, and well, of course, I mean, we speak in a linear fashion and so on, but the structure I mean, you can get a complete grasp sometimes of the functioning of some axioms by looking at them as rules. Like with the result I mentioned about decidability, by writing Aristotle's proofs in a tree form, I can answer to any question about the structure of Aristotelian proofs. It becomes completely transparent. So this is, of course, a definitive advantage. Now, axiomatic systems are very nice in some way, because if you have a rule system and you add one rule, then properties of the rule system may fail, like path elimination fails when you add something. If you have an axiomatic system and you add some axiom, well, the things that it's sort of conservative in that way. What was the case earlier remains somehow. So it's like axiomatic systems are modular in a way which that's definitely advantage. But for this kind of meta purposes you mentioned, they are a disaster for the actual representation of logic and mathematics.
Well, why do mathematicians use two-dimensional representations of this?
No, you see what mathematicians say, who is the mathematician who says, well, now I have assumed A and B, so let me use logic to conclude A, and let me use logic to conclude B. Now, they will just jump at once into these components, and they will consider them separately, not in any way like, let me first conclude A from the conjunction, then B, and so on. No, they are written because the writing has this convention, but the way you think about this is that you have now these pieces, and you can do sort of independent different things with them. Likewise, if you have like a disjunctive assumption, well, someone in California is getting this result, and someone in Japan is getting this result. There's no order in this thing, absolutely no order.
Yeah, but we just talked about, if we're talking about the way proofs are actually presented, there is very little attempt to present them in a two-dimensional format. Mathematicians use whatever representations they find on the pictures.
I don't think mathematicians ever use any axiomatic logic.
I wasn't arguing that that wasn't my point.
They would intuitively use things like, I want to prove an implication, so let me assume A, and then the task is to prove B. This would be a kind of thing.
But I don't, that's not denying anything I'm saying.
Okay.
Very shortly, the same theme, actually. So, I mean, one must distinguish between the use of this structure for studying proofs, and it's no question, as you illustrated, the enormous advantage of the free form. But when it comes to using, actually producing a proof on the object level, well, Jensen himself had made a remark that actual thinking is linear. That is what he said. That was my question I wanted to raise. It's an interesting pedagogical question. I mean, you have some kind of example, some quotations at the beginning, but you think, well, certainly the production of a sentence is linear. But the question is if the understanding is linear. So this is, I mean, there are logical questions of that kind which could be interesting to study more. So that's one aspect, more philosophical. The more technical one, again, when you use it, when you use a group, of course what is costly is that, could be that you have a long proof of some big cost when you make the linear and but the most interesting is maybe this technological question, what is the real understanding what we see.
Well, the sort of metaphysical belief is that we are two-dimensional in our brains or n-dimensional. So it's not just, in my mind, a question of representation, but it's like parallel things are going on in the head, and sometimes the creative act is to pull them together, and that's like a threefold. So it's a primordial creative act to see that this and this thing combine.
Well, that's
Well, that's to sit down.
yes. No, just one. I promised him, and then we will have to start. No. The beginning.
So, if I understand, you're saying that as long as the rule or the linear case, as long as the rule for the introduction of the conjunction allows that the line, starting line is the same, we can have the derivation like this, and we do not need the repetition, not even in this case. Okay.
But we just repeat the justification.
Okay, we agree. And then another thing that you said is that the equivalent of this in the tree case would be this. Okay, so you seem to say that there's not really a difference, interesting difference between P, therefore P and P, and P, therefore P and P. Oh, I don't want to question that. So suppose that I say snow is white, therefore snow is white and snow is white. So according to what you said, that we have this linear formalization of the argument and this trivial formalization of the argument. So it seems that in this case then we have an argument that apparently includes no repetition, and in the linear case you do not have a repetition, but in the tree case you must have a repetition. Which is, it's interesting because it's the opposite of what you were saying about the two linear.
So, I would say as follows, that to be able to conclude the conjuncts, we have to justify those conjuncts. And in this case, the justification happens to be identical for both conjuncts. So, no mystery.
And I think we will have to stop here and thank all the speakers.